Hi students, let us discuss about the thermodynamics problems in the GATE 2021. And here it is given van der Waals equation of state as PR is equal to 8 times TR by 3 times VR minus 1 minus 3 by VR square. As we already know, PR, TR and VR representing the reduced pressure, temperatures and volume. And it is also given that compressibility factor at critical point is ZC, which is 3 by 8. And the values of reduced volume, reduced temperature are also provided. What we have to find out is the compressibility factor from this equation of state you are supposed to calculate at a given conditions. So here it is represented. If you watch to the PV diagram, right, and at the topmost the peak of the PV diagram, the isotherm goes in this way. At this particular point, where if the graph is between the pressure and volume, the thing is at this particular point you can see the curve takes a turn and becomes flat at this particular point at critical state, at critical temperature. The curve goes through a flat region. At this region, the slope of this particular line is 0. It's flat, and the second derivative, okay, of this particular line is also 0. That means this is called as inflection point on the isotherm, because we are trying to take the help of this inflection point to find out the compressibility factor through the van der Waals equation of state. So at this particular point, the slope dpc by dv at Tc and d square pc by dv square at Tc will be equal to 0. That means we are going to use this particular help of this inflection point. PR equal to P by PC and TR equal to T by TC. So the thing is, we have to find out the compressibility factor Z. Okay, what is this compressibility factor? The compressibility factor is PV by RT. So let us convert this in terms of the critical pressures and reduced pressures. PR equal to P by PC. Therefore, P is equal to PR into PC. T equal to TR. TR into. Similarly, the volume also. Okay. Let us convert P equal to PR into PC. V equal to VR into VC, and temperature T equal to TR into TC. Separate out the reduced terms with respect to critical terms. PR VR by TR into PC VC by R into TC. And we know PV by RT is nothing but Z. Therefore, PC VC by RTC is nothing but ZC, that is critical compressibility factor. And we already know the van der Waals equation of state. Through this equation, we can able to figure it out. PC is equal to RTC by VC minus B minus A by BC square. A and B are constants for this temperature dependent constants. Okay. So using this expression, we are supposed to calculate that ZC. And if you know the ZC, and Z can be calculated. PR, VR, TR are already provided because VR equal to 3, TR equal to 4 by 3. If you substitute in this equation, you get the PR. That means PR, VR, TR values we can able to easily estimate. The thing we have to estimate is ZC. If you know that ZC, you can able to calculate the Z. And thing goes like this. Okay. And you can see the van der Waals equation of state, it is in terms of A and B constant. You can see RTC by VC minus B minus A by VC square. So we have to somehow calculate the ZC. Okay, that ZC, that means we have to take the help of this inflection point to calculate PC VC by RTC. That means taking out the derivative, first derivative and second derivative, we get the values of PC VC by RTC. Therefore, and for example, I'm going to show you how this has come. RTC is nothing but 8 times A by 9 times 3 into B. VC is equal to 3B. PC is equal to 1 by 27 into A by V square. Now I have got everything in terms of A and B. So once I substitute these values here, I can able to calculate the ZC. That ZC turns out to be 3 by 8. Through this ZC, using this particular equation 1, I calculated the compressibility factor is 0.843. Let us get how we have reached to the values so we can able to calculate Z. So let us start the derivation. Okay, and here it goes. Given van der Waals equation, 8 times TR by 3 times VR minus 1 minus 3 by VR square. Don't worry, I have, let us find out the values. At inflection point, I know the dou PC by dou V at Tc equal to 0, dou square PC by dou V square at Tc equal to 0. So given van der Waals equation of trade, if you take out the derivative, first derivative, you get RTC by VC minus B whole square is equal to 2A by VC cube. Similarly, if you take the second derivative, you get 2 times RTC by VC minus B whole cube and 6A by VC power 4 equal to 0. Through these equations, I can able to figure out that equation, put equation 4 in equation 5. Therefore, 2 times RTC by VC minus B whole cube is equal to 6A by VC power 4. In place of RTC by VC minus B whole square, substitute the value of 2A by VC cube. So if I substitute the value of 2A by VC cube, I get that VC equal to 3 times B. Therefore, B equal to VC by 3. Okay. And further, now I know the value of B. You can see VC times the 3, or VC is nothing but 3 times B. So similarly, take the equation 4. Now substitute in place of B, VC by 3. We have got the expression for B equal nothing but VC by 3. We substitute, and through the, let us calculate what is the value of PC. A, you can see through this equation, A is equal to 9 times VC RTC by 8. Okay. Now I know A, I know B, I know RTC, which is nothing but 8 times A by 9 times 3B. Okay, because here we can able to get from how we got this equation. Therefore, now we have got everything. Substitute in this particular term, which is PC. Now you can able to substitute in this particular equation what is, and you get everything in terms of, so let us do. Therefore, PC is equal to 8 by 9 times RTC is nothing but 8 into A by 9 times 3B by VC is nothing but 3B minus B minus A by VC square nothing but 3B whole square. Therefore, PC is equal to 1 by 27 into A by B square. So now I got everything. Let us substitute, let us calculate what is ZC. ZC is nothing but PC VC by RTC. Now what is PC is nothing but 1 by 27 into A by V square. What is VC is nothing but 3 times B. What is RTC? Nothing but 8 times A by 9 times 3B. If you substitute, you get the value of critical compressibility factor, which is 3 by 8. Therefore, the Z equal to, with the final equation, okay, the Z equation is nothing but this particular equation. Let me show you. This is the Z is nothing but PR VR by TR into ZC. So if you can able to substitute the things, finally you can calculate Z equal to 0.843. This is how you get the value of critical, compressibility factor for a van der Waals equation of rate at given conditions. Let us move to the next problem. So let us move to the question number 23. It is given molar heat capacity, that means Cp for N-pentane as a function of temperature is given by Cp by R equal to given expression in terms of temperature, where R equal to 8.314 joule per mole Kelvin. At 1000 Kelvin, we have to find out rate of change of molar entropy with respect to temperature at a constant pressure. So let us find out the rate of change of molar entropy with respect to temperature. And we know the basic equations for the entropy is a function of temperature and pressure. So ds is equal to Cp by T into dt minus dou V by dou T into dP. As we know that we have to suppose to calculate the at constant pressure. At constant pressure, dP equal to 0. So ds is nothing but Cp by T into dt. So take this temperature on this on the left hand side, you get ds by dt is equal at constant pressure P is equal to Cp by T. When you take in the derivative with respect to a constant variable, then ds by dt become dou s by dou t. That means ordinary derivative will become partial derivative. So what we are supposed to calculate? What you are supposed to calculate? Change of entropy with respect to temperature. That means dou s by dou t. Change of entropy with respect to temperature at constant pressure is nothing but Cp by T. And Cp by R is given. Therefore, Cp is equal to R into this entire expression. Therefore, Cp by T is nothing but R into this particular entire expression divided by T, which is kept it as a symbol T. So at what temperature we are supposed to calculate this rate of change of entropy with respect to temperature? I mean at 1000 Kelvin. So everything is provided. Put temperature equal to 1000 Kelvin and R equal to 8.314, and finally dou S by dou P is nothing but Cp by T, 0.280 joule per mole Kelvin square. Okay, let us move to the next problem. Yeah, let us move to the question number 38. So, okay, in essence of this particular question, I will explain you in just a simple case. I mean, there is a container consisting of carbon monoxide 1 mole, oxygen 0.5 mole, carbon dioxide 0 mole, nitrogen 2 moles in the initial state, and a reaction happened. Okay, according to CO plus half times O2 gives rise to 2CO. Okay, yeah, I mean CO plus half times O2 gives rise to CO2. This reaction happened. After this reaction, the system went to the state number 2. Okay, before this particular reaction, the pressure and temperature in the container of 1 bar and 298 Kelvin, and after the reaction, then pressure equal to we are supposed to find out, and temperature we are supposed to find out. This is the crux of this particular example. Okay, we have to find out pressure and temperature. What is the given? Given what are the initial moles before the reaction and final moles after the reaction. Here in the reaction, carbon dioxide, oxygen and react, okay, to form CO2. That's why initially there is no CO2. It is said that pure monoxide and oxygen is present, and in addition to the things which are involved in the reaction, the nitrogen is also present. Nitrogen is not getting reacted before and after the reaction, therefore it will remain, the moles of the nitrogen will remain the same. In such cases, I mean, we are supposed to find out what is the final pressure and the final temperature when complete reaction happens. And given, what are the given? The given the reference temperature, that means here the temperature T1 state is nothing but 298 Kelvin, which is also the reference state. That why it is reference state, that means, I mean, you can see internal energy change of the reaction. That means because of this particular reaction, the change in internal energy is 282 kilojoule per mole, nothing but, I mean, 282 joule here per mole of, I mean, CO getting reacted. Because 1 mole of CO got reacted, so total energy per mole of CO2 is nothing but, if you talk in terms of total energy, 282 kilojoule, because there is 1 mole of CO, therefore 282 kilojoule per mole is nothing but 282 kilojoule. The basis is 1 mole of CO. And the beauty is the reference temperature, that means, I mean, internal energy of reaction is given at reference temperature, which is 298. And here the state 1 is also at 298. So because of this, I mean, there will be less mathematical complication because the reference temperature and initial temperature both are same. Let me explain you in essence. Okay, after the reaction, okay, because of the release of this much amount of energy, I mean, a kind of here, and automatically, because here it is given, let me explain you in much better way. It is given minus, don't worry about this minus symbol. The shortcut I am going to explain you in the initial case. Later on I am going to explain you the detailed ones. So the amount of energy that is because of the reaction released is around 282 kilojoules. What happens if the reaction happens, some amount of energy got released inside the container. Because the container is insulated, what happens, whatever be the reaction energy released, it will try to increase the temperature of the products. What are the products here? After this reaction, only CO2 will be present, because CO and half O2 gives rise to CO2. So in the state 2, CO2 will be present and nitrogen will be present. What happens because of this particular reaction, which the energy which is released, it increases the temperature of this particular container, because it's an exothermic reaction. If there is no heat that is coming out of the system, all the heat that is released will increase the products, which is product is CO2 and inert is nitrogen. So this is what the basis we are supposed to take. The temperature estimation, how we can let us, the first point is to estimate the temperature for the state 2. To estimate the temperature for the state 2, we have to use the simple relation. The energy released because of this particular reaction will increase the temperature of this carbon dioxide and nitrogen to higher temperature. So that is why 282 kilojoules of energy which is released, so which will increase the temperature of CO2 and nitrogen. How we can calculate the temperature of the nitrogen? Sigma mCv dt, because it's an ideal gas, and kind of the change in, you can represent in, because it happens at a constant volume, let us presume, and sigma nCv dt. What is N constitute? What is the in the state, whatever the molecules that are present after the reaction, which is CO2 and nitrogen. If I expand the sigma, the energy is released will be equal to the temperature which is gone rise for the CO2 and N2. So N into Tr to T2 into Cv of CO2 into dt plus N of N2, moles of N2, and Cv of N2, Tr to T2 into dt. So using these relationships, I know the reference temperature which is 298 Kelvin. I know moles of CO2. I can able to calculate what is specific, Cv of CO2, because here the information is given in terms of constant. Cp is given. You have to calculate Cv. So Cv can be calculated with respect to Cp minus Cv equal to R. Therefore, Cv equal to Cp minus R. Using this information, I can able to calculate the Cv of carbon dioxide and Cv of nitrogen. So I can able to find out T2 temperature by arranging this mathematical expression. So I get the temperature, okay, from this equation. So how to get the pressure? Here you can see the volume before the reaction and after the reaction not changing, because it's a rigid insulated container. So initial volume of the container equal to final volume. If you know because both gases behaves ideally as it is provided in this example, and the volume is equal to a volume at the state 1 is total moles in the state 1 R into temperature T1 into pressure T1, which will be equal to the total moles in the state 2 R into temperature T2 and the pressure P2. Therefore, from this information, P2 is nothing but NT2 by NT1 into T2 by T1 into P1. I know moles that is remained after the reaction, and T1 moles before the reaction. T2 I got from this particular temperature estimation. T1 which is given 298 Kelvin. P1 which is also provided 1 bar. So from this information I can able to calculate the pressure. This is how you can able to go through the solve the example. It's a very crude way, this relationship, because there is an actual procedure that you have, that one can follow to estimate, because it is easy, because the temperature and reference temperature, that means state 1 initial temperature and reference temperature both are same. So there will be easy for us to calculate. What happens if the initial temperature is also different from the reference temperature, then there is a specific procedure we have to follow. Let us discuss about that particular specific procedure. So you can, this is the same information, initial state, final state, reference temperature, okay. The change in internal energy, a standard change in internal energy because of the reaction is also given at 298. State 1 is P1 T1, state 2 is P2 T2. We have to take the help of first law of thermodynamics for a closed system to solve this particular example, because it is said that insulated container, so Q equal to 0, change in internal energy, because from the state 1 to state 2 is nothing but delta U, and from this the heat that is exchanged with the surroundings equal to 0, and work that is also 0, because there is no shaft work, expansion work, no work happens because of the change of the system from state 1 to state 2. Therefore, put everything in this closed system, we get change in internal energy equal to 0. That means this is how the things in general, how you have to follow the procedure. And because you are taking the system from state 1 to state 2. During this change of the system from the state 1 to state 2, it has followed delta U equal to 0. Okay, the change in internal energy is equal to 0. So you have to estimate the state 1, state 2 temperature and pressure for a given state 1 temperature and pressure. If the reference temperature is not same as initial temperature, because reference temperature is given as 298, and initial temperature, because both are same. If it is not same, you have to follow this particular procedure. First of all, because change in internal is the state function, so for you to calculate this path, you can follow the alternative path. Okay, first cool I mean, because if the reference temperature and initial temperatures are different, first of all you need to cool the system to reference temperature. That means cooling of this reactants plus inerts to the 298 Kelvin. Then you conduct the reaction at reference temperature, because the value of change in internal energy of the reaction is given at 298 Kelvin. That means you need to cool down the reactants and inerts to reference temperature, conduct the reaction, and again increase the products. That means these are our products which are at different temperature. So heating of the products and inerts from reference temperature to the state 2. Instead of going through this path, which is unknown path, we have followed the path which is known: cooling, reaction, and heating. There are 3 different steps. Even though in both the routes, blue as well as black, the change in delta equal to 0, because it doesn't depend on the path you follow. The change in internal energy depends on the initial state and final state. So, and there is one low complexity, because the initial temperature and reference temperature of the same. That means now the figure looks like this: state 1 to state 2, delta equal to 0. State 1 is also at reference temperature. To calculate this, there is no cooling of the reactant step. Simply conduct the reaction at T1, which is reference temperature, and heat the products and inerts from TR to state 2. That means it's a simple path. There is no cooling of the reactants. It is simple. Conduct the reaction at TR and increase the products and inerts to the state 2 temperature. So we have to follow this particular path. Okay, let us do this particular path. Okay, this is how the things in general. Delta equal to 0, that means state 2 internal energy minus state 1 internal energy equal to 0. How to calculate the state 1 internal energy? Internal energy can be estimated using this particular equation: Ni into Ui. That means moles of I into, and you can see standard state internal energy of that particular I, plus N into Cv into dt. This is a standard equation to calculate the internal energy of any particular state. You can use this particular equation. Let us apply this particular equation to all the things. Okay, and let us take first of all U1. That means internal energy of all the molecules of the system in the state 1. Okay, let us expand. So here the second term will be 0, because T1 equal to TR. Here in this example, the state 1 is at reference temperature only. So in such cases, the dt, T1 equal to TR, so dt equal to 0. That means to estimate the internal energy of the system in the state 1 is simply with the first term. Let us, what is I representing? I representing the 4 molecules. Carbon monoxide, because these are the at any point of time these 4 are present. So what are these 4? Monoxide, oxygen, nitrogen, and dioxide. Let us expand this particular sigma, because there is a sigma term will be there. Okay, this is particular sigma for everything, because there are more components are present. If you expand this particular sigma to 4 components, one is NCO into UCO, that's state 1, NO2 into UO2 for the state 1, because you are doing it for the state 1, N for nitrogen, and U for nitrogen, N for CO2, U for CO2 for the state 1. So this is what the standard equation you are supposed to calculate U1, internal energy of the system for the state 1. Similarly U2. U2 is nothing but same equation applies. Now T2 is different from reference temperature, because after the reaction the temperature again has increased. That means your reference temperature has gone up to the T2. That means you have to consider the second term also. Let us this expand this particular sigma this to 4 molecules. Okay, if you expand this to 4 molecules, you can see first 4 terms are for this, next 4 terms are for the second term. Okay, and let us subtract the U2 minus U1 for equation 4 minus equation 3. If you rearrange the things and array, N of CO2 U of CO2 minus N of CO1 to UCO minus N of O2 state 1, because I have arranged in particular way so that I can able to get the expression that is required. So I have kept state 2 minus state 1 because the things which got reacted, that means CO plus half O2 gives rise to CO2. Okay, this is the particular equation. So accordingly, the given is change in internal energy of the reaction is given. What is change in internal energy of the reaction? Carbon dioxide internal energy minus carbon monoxide internal energy minus oxygen internal energy. If you do this, you get the change in internal energy of the reaction. So that's why I put CO2 in the state 2 at the first, and CO and oxygen which is there before the reaction, and this is after the reaction, and rest everything I have arranged. Okay, because this is what that is given, change in internal energy of the reaction which is provided. Okay, here remember this, and let me simplify the things as easily as possible. If you take this first three terms, let us take the first three terms. Okay, the first three terms in which what is the number of moles of carbon dioxide in the state 2 is 1 mole, and carbon monoxide in the state 1 is 1 mole, and oxygen in the state 1 is 1 mole. So this equation is nothing but change in internal energy of the reaction which is provided. That means in place of first three terms, I can able to put delta U of the reaction which is given, and for the rest terms, nitrogen in the state 1, in the nitrogen in the state 2 equal to 2, because nitrogen is inert, it is not getting reacted. What is oxygen and carbon monoxide in the state 2 is 0, because after the reaction there is no oxygen and no CO present in the state 2, that is why it is 0. Similarly, carbon monoxide carbon monoxide is equal to 0, don't worry, right. CV, but both are same terms, don't worry. CV is a constant. Okay, CV, that means internal energy, change in internal energy depends on the CV. Okay, CV doesn't change with the temperature. So integral TR to T2 CV dt, CV can come out of the integral. Okay, if CV can come out of the integral TR to T2 CV dt is equal to CV into T2 minus TR. If you apply this particular for in every molecule, you can bring this CV out of this integration, and few things are 0. The first three will become internal energy of the reaction, rest few terms are 0. Okay, next, change in internal energy, the only three terms will remain in the earlier equation, only change in internal energy of the reaction in N of CO2 TR to T2 CV into CV of CO2 into dt plus nitrogen moles into TR to T2 CV of nitrogen into dt equal to 0. You can see that big equation transforms to only 3 steps. Okay, let us further. If you rearrange the equations, that means common this T2 minus TR from this equation, bring it to the left hand side, rest everything to the right hand side. Finally, the change in temperature is nothing but minus delta U of reaction divided by moles of CO2 into CV of CO2, moles of nitrogen into CV of nitrogen. Moles of CO2 and moles of nitrogen in the state 2, it is already there. Okay, carbon dioxide is 1 mole and nitrogen is 2 moles. So from this equation you can able to calculate what is the temperature 2, okay, in the state 2. Given Cp of nitrogen can be given and Cv of nitrogen can be calculated using this equation. Cp of CO2 is given, Cv of CO2 can be calculated using this particular equation where R equal to 8.314 joule per mole Kelvin. Delta U, change in internal energy of the reaction, is given minus 282 kilojoule. It is nothing but 282 into 10 power cube joule. Temperature is 25 degrees centigrade. Is 298 Kelvin. So everything is every value is known in this equation except T2. So calculate T2, which is 2845 degrees centigrade. Finally, we have arrived to the conclusion. What is the temperature in the state 2? Let us calculate the pressure. Okay, the pressure is calculated. You know this is state. Now we know what is the temperature in the state 2 is 3118 Kelvin. Using this expression V1 equal to V2, final P2 can be calculated using NT2 by NT1 by T2 by T1 into P1. What is NT2? Total moles after the reaction, which is 3, and T1 is the total mole before the reaction, which is T.5. T1 and T2 already known. P1 equal to 1 bar. Put it in this expression and calculate P2, which is 8.968 bar. This is the how we can able to logically solve the problem in a longer derivation. Thank you. Let us move to the next problem. Let us discuss about the question number 39. In crux, it is given there is a container consisting of 80% of inerts and 20% of CO2. Somehow you have to separate by CO2 and inerts. Keep a membrane or anything. Finally, it should be separated. On one side, it should be 80% inerts. On the another side, it is 20% of CO2. Somehow you have to separate these two. And if you think the other way, let us solve this problem in the other way. Okay. There is a container which is separated by membrane. On one side, it is 20% CO2 and 80% membrane. Suddenly, you have removed the membrane. Both got mixed to form 20% CO2 and 80% inerts. So it's a simple, if you think of this reverse process, it is a separation. Now this particular process is the mixing. So in general, mixing is easy. So let us solve for the mixing. What you are supposed to calculate finally is what is the work required to separate the CO2 and inerts. Okay, I want on the one side it should be pure CO2, on the another side it should be 80%. That means from a mixed state I have to separate these two, that is pure CO2 and pure inerts. To do this process, how much of work I have to put on this particular system to get this particular separation. How we are going to approach the problem is the reverse. Let us assume I have some container which is CO2 and separated by the inerts. I remove this particular membrane, both will get mixed. That means if I do this path, I am getting the work for the mixing. Okay. On the other path, it's a work for the separation. If I calculate the work for the mixing, which is the minus of the work for the separation, that means if I calculate work for the mixing, which is nothing but the minus work of the separation. That means if I am supposed to calculate how much work that is required to separate the CO2 and inerts, that means if I calculate the work for the mixing, it is a minus of the work for the mixing is nothing but the work for the separation. And for ideal gas, let us assume this is a unmixed state and mixed state. If I take the system from the unmixed state to mixed state, the unmixed is state 1 and mixed is state 2, then the change in entropy, before before I calculate the work, I should know what is the entropy of the mixing. Because the entropy of the mixing, that means from this to this state, minus I can calculate the change in entropy mixing minus R into sigma xi ln xi. This is the standard formula. The entropy change of mixing, xi is the fraction of CO2 and fraction of the inerts in the mixture. We have to take the help of the thermodynamic first law to estimate the how much work that is for the mixing that has occurred. I know for the ideal gas, the change in internal energy is nothing but Cv into dt. Because it is said that occurs at the same, because this mixing process should occur at the same temperatures and pressure, because internal energy is specifically depends on the temperature. When the temperature is dt equal to 0, du equal to 0. That means in the first law, the du equal to 0. Therefore, dw is equal to minus dq, and we know and the entropy relationship with respect to the heat, minus dq. dq is nothing but T into ds. Therefore, dw is equal to minus T into ds. If you integrate, okay, then total work, okay, if you integrate this expression from the state 1 to state 2, you get state of mixing, the work for the mixing to happen is nothing but minus T into entropy change. Entropy change of mixing you can able to calculate with this expression minus T into minus R into sigma xi ln xi. So what you need to do, you are supposed to calculate separation. The separation, work for the separation is nothing but minus the work for the mixing, that is equal to T times R xi ln xi. So using this expression you can able to calculate the work for the mixing. Okay, let us do in the deeper state. You can see, okay, this is what the expression. delta equal to 0, dw is equal to minus t into ds, because ds equal to dq by t. If you substitute in this particular expression, and you get integrate w1 to w2, s1 to s2, and s1 s2 are the state 1 state 2 entropies, w1 w2 are the, and if you integrate, w2 minus w1 is equal to minus t into s2 minus x1. This is net work. W2 minus W1. The difference between these two is nothing but net work, which we are supposed to calculate. Net work is minus T into S2 minus X1, which is delta S. Delta S, the change of entropy, is nothing but entropy of mixing minus R into sigma Xi ln Xi. R is given. X of CO2 is 20%. Inerts is 80%. If you plug in this particular equation, the entropy is 4.160 joule per mole Kelvin. Okay. Then work, okay, net work, okay, you get is minus T into ds. Temperature is at 300 Kelvin, we are calculating. So T is 300 and delta S is 4.160. Finally, net work, okay, for this mixing is nothing but minus 1248.103 joule per mole. So here we got the work for the mixing is joule per mole, but what we are supposed to calculate is total work. Total work is, because in total it is given that in the mixer total 100 moles of inerts and CO2 are present. So nothing but minus 1248.103 joule per mole into 100 moles. That means total work in this mixing process is minus 124.81 kilojoules. But what we are calculate? Work of separation, which is minus of the work of mixing. So the work for the separation is 124.8 kilojoules. That means you are supposed to provide this much amount of work to separate this mixed state to unmixed state. Okay, I hope you got the essence. Let us move to the next problem. That is question number 40. Okay. And it is said that a binary liquid mixture consisting of two species, that means they are talking about the binary mixture. Let's gamma and x represent the activity coefficient and mole fraction of the species. Using molar excess Gibbs free energy model, that is, ln gamma versus x1 and ln gamma 2 versus x2. Using this particular information, okay, we are supposed to find out what is we are supposed to find out slope of tangent drawn into ln gamma 2 versus x1. That means somehow you have to find out the slope for the plot ln gamma 2 on the y-axis, x1 mole fraction of 1 on the x-axis. That means this is how. If you plot ln gamma 2 on the y-axis, x1 on the x-axis, if there is a curve, you have to find out what is the slope of this particular curve. The slope of this particular curve is dy by dx. It is nothing but d of ln gamma 2 by x1. This is what we are supposed to calculate. What were provided? And it is provided the tangent drawn ln gamma 1 versus x1 curve at the mole fraction of x1 equal to 0.2 is nothing but slope. Okay, that means it is provided ln gamma versus x1. Okay, the slope is provided here minus 1.728. At what particular point? At x1 equal to 0.2, the information about the slope information, that means d ln gamma 1 by dx1 is provided, which is minus 1.728. Using this slopes informations, using this given slope information, we are supposed to find out this particular slope information. And we are going to take the help of a Gibbs-Duhem equation. Gibbs-Duhem equation states that sigma xi dm bar I is nothing but dou m by dou p into dp, dou m by dou t into dt. Don't worry about this particular right hand side term, because we are trying to calculate at constant temperature and pressure. So we are using the Gibbs-Duhem equation at constant temperature and pressure. Therefore, dt equal to 0, dp equal to 0. That means right hand side expressions will be equal to 0. Only one term remains, xi dm bar I equal to 0. What is m bar I? M bar I is the partial property of a component. Here, what is the partial property we are looking about? Ln gamma 1. Okay, this is the ln gamma 1 is the partial. In place of m bar I, substitute the values of ln gamma 1. Because this is a binary mixture, if I expand the sigma, I have to expand to two components. x1 d ln gamma 1 plus x2 d ln gamma 2. Okay, because in place of m, we have to substitute ln gamma. So if I expand the sigma, let us divide this equation 3 with respect to dx1. Therefore, x1 is equal to d ln gamma 1 by dx1 plus x2 ln d gamma 2 by dx2 equal to 0. x1, sorry, both are x1 because we are divided with x1. So one information is provided, d ln gamma 1 by dx1 is given minus 1.728. We are supposed to calculate d ln gamma 2 by dx1. So if you rearrange this equation, you can able to find out d ln gamma 2 by dx1, that means slope informations of this particular graph is minus x1 by x2 into d ln gamma 1 by dx1. x2 is given, okay, x1 is given 0.2, x2 is nothing but 1 minus 0.2, which is 0.8. So the slope information is 0.432. This is what that is information required. The slope of the tangent drawn to the curve ln gamma 2 versus x1. So now, okay, this completes the story. Thank you very much.